Why do you think people are so excited about inference right now?
Scaling laws, the beta lesson, like everything that these AI researchers got scaling pilled about over the last few years, like the downstream effect is inference becomes much more valuable and much more complicated.
The space is so early that people from all kinds of different backgrounds can come into this space and make genuine contributions. You don't have to have a PhD to become an inference engineer.
It's interesting because I have seen in the news a lot, obviously from recent events like government control of AI versus Anthropic or OpenAI, but what I haven't seen talked about so much is like the fundamental question of who controls AI with open models versus closed.
There is an argument to be made against having one or two individual organizations control all of that power. Will have drastic repercussions for the rest of the world.
Philip, you just wrote a book on inference. Your launch post got over 3 million views. Why do you think people are so excited about inference right now?
Well, you're the one who's always talking about big token, right?
Yeah.
Everyone's trying to get away from big token. You have one version of the AI industry that, for the last couple of years maybe looked like it was going to happen, which is, you have 2 or 3 companies out there that make models and need to run inference on those models to serve a whole plethora of vertical applications who are renting their intelligence a token at a time. But now everyone's realized that if they're able to create their own models, they're able to do fine-tuning, post-training, even training new models from scratch. And if they're able to combine that with the ability to run those models at scale with leading latencies, with high reliability at low cost, then they're actually able to build much more differentiated AI products. And so now every company is developing an inference strategy, and every engineer is realizing, wait, this is a very valuable and in-demand skill set that I have the opportunity to learn today, where in a couple of years, there's just going to be massive demand for people who know how to do this.
Okay, I want to take it back a little bit. For anyone who's watching and doesn't know, what is inference?
Inference is everything, right? Inference is what runs the models that every AI company relies on to power their products. It's the process of taking a model, getting a GPU, putting the model on the GPU, and making it run fast. And it sounds very simple when you say it like that, but it's actually a pretty complicated process.
Yeah, and I like your example of when you write something to ChatGPT and the response coming back being served inference.
Exactly,
Yeah.
Exactly. Anytime the AI model is actually doing something valuable, it's inference.
Yeah. So you've worked at Baseten for 5 years, right?
A little over 4 years.
Okay.
Yeah.
So you were working there before even ChatGPT came out.
That's true.
Can you talk a little bit about the history of inference and how it's shifted and why it's becoming such a valuable skill?
So inference used to be not easy, but much easier. It was taking a model trained with something like XGBoost, maybe a early BERT model, something with, at the largest, a couple 100 million, maybe 1 billion parameters. And you're running it generally for some low volume internal use case, some kind of classification dashboard or whatever. And you're running it either on a CPU or maybe a T4 or an A10, one of the smaller low-cost GPUs. It just wasn't a very large-scale, very critical workload. But as models became more sophisticated, they got larger. Whisper came out. That was a couple billion parameters. That's a huge model. And now all of a sudden, you need a whole A10 just for this one model. And then, large language models started coming out, diffusion-based image generation models. Models got bigger and bigger. Now they're 10 billion parameters, 100 billion, 1 trillion parameters. You start needing more and larger and more sophisticated GPUs, as well as a software stack that goes all the way from the CUDA level up to the inference engine to the serving orchestrator, as well as on the infrastructure side, everything you need to do to provision now thousands and thousands of very expensive and valuable GPUs, keep them running, keep them serving traffic, and make sure that, when things happen, you don't drop valuable requests. Mm-hmm. So, over time, inference has gone from something that was like fairly straightforward and achievable with a small engineering team to something that is both mission critical for a large number of incredibly valuable and successful companies, as well as very complicated, relying on a stack with literally dozens of different technologies across engineering specialties.
Yeah. And I feel like this is really downstream of all like the AI research that people now see as quite famous and notorious in like frontier labs and that sort of stuff. I think people like to focus on that because it's the cooler side of things. But, you know, scaling laws, the bitter lesson, like everything that these AI researchers got scaling peeled about over the last few years, like the downstream effect is inference becomes much more valuable and much more complicated. And things like mixture of experts and all these like wacky ideas that the researchers come up with, and then kind of the inference engineers are left to figure it out, because at the end of the day, what good is a model if you're not able to run it on GPUs and able to run it efficiently? So I think inference is becoming just as important as the actual research itself, because it's so tightly coupled with it.
Absolutely. And another thing that makes inference really hard is, you know, you're a researcher, you know what research code is like. It's not necessarily a 5 nines of uptime type of code base that usually gets published. In a lot of industries, you have months or years or decades even from research to get into production and get into production at scale. But in the inference industry, a new paper comes out and we might be implementing it within a couple days.
Yeah.
So the space moves very fast, and you have to take all of these new concepts and make them bulletproof in production very quickly.
Yeah. I mean, like, I think, you know, the DeepSeek models are a great example of this. Like, they're constantly pushing the frontier. They're trying things like lightning indexes and sparse attention and all these sort of wacky ideas that are designed to make the model as smart as possible, but they certainly don't make the inference engineer's job very easy.
It doesn't. In fact, actually, one of the things that we do with DSA is sometimes we just turn it off so that, you know, on shorter context requests, we just don't have to deal with it because it's actually less efficient at certain context lengths.
Charlie, can you go back to what you said on research and talk a little bit more about the research side of things and like its relationship to inference and demand for it?
Yeah, I think there's people kind of assume that the demand for inference is going to grow linearly with user adoption. And I think what we're seeing on the research side and the directions people are pushing in, that's not the case anymore. It's much more combinatorial in a bunch of factors. So the first thing is these like huge kind of agentic workflows. It's not the case anymore where we're constrained to kind of this chatbot style setup where you put in a request and you receive one request back from kind of one copy of the model. Now it's much more, you put in a request and it's usually like to do with a code base or like some sort of enterprise workflow, and you'll spin up a bunch of agents which run and go and like do tool calls and like go search the internet and even spin up their own sub agents to do things. And so the amount of like compute we're putting in per request has grown exponentially. And then there's kind of a related idea, which is this idea of like search time compute. When it first came out with the O1 reasoning model and kind of RLing the models to be able to like do more thinking at test time became the dominant paradigm, and that has been very successful for a number of reasons. But now we're seeing these like very parallel work streams where, for instance, like we know that the Gemini kind of pro research models and even the OpenAI and Anthropic ones are speculated to do the same thing, have a lot of different parallel streams. And so again, one request is multiplied into many, and the inference on that side becomes even more complex because a lot of these agents are retrieving the same information, looking at the same parts of the code base. They have their own KV caches, which are expensive both to store and to prefill. So how do you manage the inference on that side? And it's both a hardware problem and a software problem. And then I think the final thing that is like really interesting is context windows and its relation to like continual learning. So the context windows have grown a lot since we first came out. I think when we got 32K context windows for GPT-4o, everyone was like, wow, we will never need more than this. This is awesome. And then now people are kind of demanding billion token context windows. We're still only kind of at the million token mark. But regardless, context windows are growing. This idea of compaction is also this really kind of interesting direction which people are pushing in. We know we want the models to continually learn, at least to the extent that we can have very, very long context windows where you can kind of shove in enough information such that the model learns a whole job on the fly. And then this has implications for inference as well, because suddenly you don't just have this very static KV cache for one model. You obviously have all the parallel stuff I talked about before. But now if we're compacting the KV cache and we're passing that around between a bunch of different models, it's like that is an incredibly difficult inference engineering problem. And you solve that at the hardware layer. And I think we're seeing NVIDIA do this by making bets across a bunch of different kind of like new architectures for the hardware to run these models. But you also have to solve it at the software layer, which is like, how do you pass these huge cases around across multiple agents efficiently, and kind of maximize throughput, minimize latency, maximize reliability, and that sort of stuff.
Absolutely. So just to kind of summarize those factors, let's make a list, because it seems like we have something like 10 factors multiplied together. There are more models. These models are bigger. There's more demand for them. They have longer context windows. Within the demand, every time they run, they're running multiple times. And then you're saying that they're also now running within each of those multiple runs, potentially in ways that interact with each other, and share resources between each other. And then I think there were a few more factors in there
like
as
tool
well.
calls, tool calls now often return so much information, which is just like getting dumped in the context window. Even though the actual model itself, like one individual call might be getting cheaper. As that happens, people aren't using the model the same amount or less. They're actually just demanding more because it is cheaper. And I think like that is really playing out on the inference side. Like inference is just growing like combinatorially, basically, in all those factors.
Absolutely. And one thing I wanted to touch on is you mentioned the idea that NVIDIA is working a lot on solving some of the, problems around KV cache sharing. We work a lot with the Dynamo team. We were one of the first adopters of Dynamo as a toolkit. And some exciting stuff from that is we've got now the ability to move KV cache around different levels of memory, as well as PD disag. And I think that the disaggregation piece is something I wrote about. It's something I'm really excited to see more in the next year, because prefill and decode are just very, very different workloads that just happen to run together because they're both necessary, but they're just completely different shapes.
Yeah, and I don't think you can assume that the balance of that workload split between prefill and decode is going to remain the same. Like it definitely hasn't so far, like for all the reasons I listed before. Like we're seeing these kind of fundamentally different workflows with much more agentic backbones. And that really changes like what the prefill burden is versus the decode burden is. And I think that's only going to continue to change. I imagine like a naive guess would be that these things just continue to scale up. And even if that just happens, like there's going to be like fundamental challenges with how you manage this. And I think NVIDIA realizes this, and there's a reason they're making bets across like multiple different types of hardware. Jensen's smart enough to kind of at least guess where things are going. But there's the software to support that as well. And like we want that to permeate throughout open source. And there's obviously like a lot of inference engineering work to do that.
And it's hard because like even things as simple as the nature of the traffic changes the performance of your system from an inference perspective, right? Like you've seen when we do our model APIs, some of the great results we get are partially because we have, folks like OpenCode using them, and they have a lot of code agent type use cases. And in these cases, you have the shared context request over request, and then the KV cache reuse becomes very valuable. And we see really awesome performance uplifts from that. But at the same time, like if you get a piece, a request that you're just not ready for, like if, for example, you have a speculative decoding algorithm and your speculator model is trained entirely on code syntax, and then someone asks you to write a poem, like your speculator model is just going to get it wrong, and you're actually be slower than you would have been otherwise because you have the overhead of running that speculator. So there are so many different factors that go into inference, and so much of it has to get to a point where it gets computed dynamically. Your inference system can adjust in real time to the nature of the traffic coming in, rather than being something that you set up once and deploy. That I just don't see this space getting any simpler or any easier in the immediate future. I think it's going to get harder and more complex and more valuable, and there's going to be more interesting engineering work to do.
Okay, let's talk a little bit more about the book. All of that said, what are you going to learn when you read the book?
The thing about inference is it's not just one technology, right? Like there's all of these different options and trade-offs and layers. And so the first thing that this book is it's just a map. It's a map of all of the different technologies and how they interact with each other. But beyond that, it is a thesis on inference as a space and the idea that like you don't have to have a PhD to become an inference engineer. You know, I'm sitting next to someone with a whole lot more academic credentials, but the space is so early that people from all kinds of different backgrounds can come into this space and make genuine contributions. So the real point of this book is to say that inference is very early. Here is kind of what's happened so far. It's, you know, it's not that thick of a book. It's, you know, maybe it's 250 pages. You can get through this in a long weekend. And once you have, like, the world of inference is wide open. There are so many novel and interesting and deeply technical challenges left to solve in this space that once you get that, you know, basic familiarity with all of these technologies, you can figure out what's interesting to you and you can run in that direction and build something awesome.
Yeah. And I think you made a good point as well. Like, inference engineering isn't just for inference engineers. Like, in the old days, like, people like my team at Baseten doing post training wouldn't have to interact much with the inference side of things at all, right? And like, you're doing fairly simple vanilla SFT. You're not really relying on any inference workloads. But I think RL's fundamentally changed that. Like, in order to RL, you need to be able to run a model very efficiently and do rollouts at scale because the model is on policy. It's generating its own kind of responses for us to give rewards to. And so now we have to think a lot about inference, even though we're not inference engineers and like researchers are coming across this problem. So it is not just like the people working on the hardware or like the, you know, like the CUDA and the all the sort of inference engines that you talked about. It's the people using those systems interacting with them as well.
Exactly. You know, at minimum, if you read this book, you're going to be able to ask the right questions and you're going to be able to know what you're shopping for when you go get an inference system. And at most, you know, then you're going to be able to go and build it yourself.
Yeah. A lot of people who downloaded the book or reached out to me about the book are kind of people who are working as software engineers and they're trying to like transition into like working in AI or working in inference. Do you guys have any thoughts on like advice you might give to them?
Yeah, I think there is an interesting nuance point here, which is that a lot of like raw technical experience and skills has been devalued somewhat. I think when you can go to Claude or GPT and like kind of ask these types of questions, then the ability to have like all these like papers from the last 20 years loaded in your head is now less valuable. I think what is more valuable now is this kind of more qualitative creative intelligence and problem solving. I would say like don't necessarily put much stock in pedigree or experience as much as we used to, at least. I think tools like LLMs allow you to learn things exponentially faster than we could before. And so it's going to be the individuals with the most interest in those problems who are going to learn this new field. Like, we can basically throw away most of deep learning expertise from the last 20 years. And most of it doesn't apply to the things we're seeing with LLMs. And so if you are interested in this space, then learning things like inference engineering and learning about the right questions to ask is the most important thing, because now anyone has the capacity to like answer those questions and push ahead in that front.
Absolutely. I mean, this is everything that I've learned in 4 years at Baseten in one book, sure. But at the same time, I didn't have any AI background when I joined Baseten, and I still am like a little bit shaky on what exactly makes a neural network convolutional. But I don't really need to know that to do my job every day. I have more of a higher level of abstraction on the tools that we use for the modern architectures rather than a sort of deep academic background in the entire history of the space. But one thing I will say, you know, you mentioned the idea of language models and AI tools taking over a lot of engineering work. Sure. I mean, I tried to get AI models to help me write this book. They did a pretty bad job. I'm sure that's not going to remain true for very long. Hopefully someone's training the next iteration to fix it. But the level of knowledge that language models had about inference engineering concepts, I found remarkably low as I was writing this book. And I think a lot of it was because they were pulling so much old school ML ops ideas and old school, you know, traditional deep learning ideas in and trying to apply them to today's field, that in some ways there's almost an advantage to being a little bit blind to what you don't know and being able to just go in and learn what is happening today rather than everything that's happened up until now.
There's a lot of demand for inference, and it's being driven by open source models. And this was different a few years ago. Can you talk about why that is?
What we've seen is closed models came out to an early start and they got huge adoption because as the model got better, as each of these models got better, they unlocked new capabilities in the coding space. We could have tab completion, and then all of a sudden we could have code generation, and then we can have agentic coding systems, and now we have code PR review and all that sort of stuff. When you cross each of these capability thresholds, you have the model's intelligence growing linearly-ish, let's say, over time, and you have steps. And once you cross that step, you are there. Like, the model doesn't have to get any smarter to do that task. The benchmark is fully saturated. You're capable of doing the task. So closed models have been getting smarter like this. Open models have also been getting smarter like this, just a few months behind. And there's a lot of debate of like, oh, are open models ever going to catch closed models? And it doesn't really matter, because they're still crossing these same capability thresholds. And once they cross a threshold, then you can take a task that used to be on an expensive and slow closed model and switch it over to a fast and inexpensive and reliable open model. And all of a sudden your product is just as smart, but now it's substantially easier to scale it, and it's a just better user experience. And now what's happening is that people aren't content to sit around and wait for open models to catch up for whatever valuable tasks they're spending tens or hundreds of millions of dollars a year on inference for closed models on. Instead, they're coming to Charlie and they're saying,
yeah, like I agree with that point in general, that if you have a given task and the open source model a few months after the closed source model comes out is able to saturate performance on that task, I think there is an element of like demand for intelligence is fairly inelastic. Like, people always want the most intelligent model to be doing what they're doing, and they will expand the complexity of their workflows in order to use the most complex models and get the most out of these LLMs. I think the previous kind of rationale behind closed source is going to win, and Dario said a lot about this, is if you look at the base open source models versus the base closed source models, like fundamentally the economically valuable tasks that an open source model can do are a subset of the ones that the closed source model can do. But I think in the last few years, we've come into this paradigm of like, okay, that's the wrong thing to be comparing, because that's not apples to apples, because the thing you can do with an open source model is, as you said, specialize it. And so suddenly the number of economically valuable tasks that the open source models can do probably actually subsumes that of the closed source models. Like, if you are focused on a particular workflow, we now know you can get one of these open source models to outperform, the biggest reasoning models from the frontier labs and the latest reasoning models from the frontier labs. And so I think once you acknowledge that this is the case, like, it makes sense that we live in a world with specialized models. And the only way to specialize models really at the moment is through open source, to have full control over that. Saying that, I think like the frontier labs will probably eventually come around to this idea of specialized models, but that only strengthens the thesis, right? Like, if we are in a world where like enterprises are doing very repeatable things and they care about cost and latency and all those sort of things, yes, but fundamentally at the end of the day, they care about quality, then the economics 101 argument is that specialization is going to be something that happens, and we're going to see this whole ecosystem of models out there which are like doing different economically valuable tasks and kind of patching over all the possible tasks in the economy. Frontier labs are trying to do this by training on a bunch of different environments, right? And like getting as many environments from a core and these types of guys, so that they can kind of build these behaviors into the model. But at the end of the day, like, the argument still holds. If you are just focused on one particular task and going to specialize, you're always going to beat a general model.
Absolutely. And then a world with those 1 or 2 gigantic frontier reasoning models, that's the world where you don't really need a lot of inference engineers. But in your world with millions of specialized models and everyone owning their own intelligence, that's where everyone who has a specialized model also needs an inference strategy. Yep. And needs people who understand inference to get there. Yeah,
and at all levels of the stack as well. Like, in the same way that AWS sprung up to solve a lot of problems in those areas, like, we are going to see services like Baseten spring up to at least abstract away the really, really hard parts of this, but we're still going to need people to be able to understand it in order to interact with these systems and deploy the models. And so when we're talking to customers, people know what they're talking about and able to get the most out of our services.
Makes sense. You kind of touched on this earlier when you said big token. Can we talk a little bit more about what big token means? And I know we've talked about the economical reasons for why open source models are doing so well and their rise, and like the practical reasons, but also like, why do you personally believe open source models are so important for the future?
To me, like, AI is an incredibly powerful tool. And there is an argument to be made against having one or two like individual organizations control all of that power. I think like just the absolute amount of variance based on the decisions that those two organizations, let's say, are going to make will have drastic repercussions for the rest of the world. I think like one of the safest systems that the Western world has is like some form of democratic decision-making process. And I think like AI is probably one of the technologies that humans have come across that would benefit most from that democratic decision-making process. And so I think diffusing that kind of consumer surplus or benefit throughout the economy such that people are able to control their own models, benefit and profit and deliver value with their own models is a much better world than saying, okay, we have to rely on GPT-N or, Claude M or whatever the latest like closed source model is, and the decisions that those frontier labs are making around how these things are deployed and what tasks we can use them for and so on. And I think there's been a lot of stuff in the news recently with this debate. But yeah, if it is the case that like we are making decisions as like, a country, a civilization with the tools because everyone is able to access them, control them, fine tune them, specialize them, deploy them, do inference with them, then that's kind of a majority vote on the ways in which we think we should be able to use them. And that system has worked before, and I don't see any reason it should change with AI.
Yeah, it's interesting because I have seen in the news a lot, obviously from recent events like government control of AI versus Anthropic or OpenAI. But what I haven't seen talked about so much is like the fundamental question of who controls AI with open models versus closed, it seems like.
Yeah, I agree. I think there has been some of this debate in past. I think like a lot of the Chinese open source models are frequently the strongest open source models. And I think there has been a hesitancy from US enterprises to invest too heavily in open source because of that. But like there's some really exciting companies, American companies doing a lot of cool pre-training work with open source models, and they're planning on kind of releasing them this year. And I think that will fundamentally change as well. Like when you do have American open source models, which are like SOTA and competing with the Chinese open source models, then I think like a lot of this like political friction kind of goes away, and you are able to get companies in the US to buy into open source much more heavily. And I think that will happen as well.
Absolutely. That's why, models like the Mistral Large 3 GPT-OSS, we still see a ton of demand for these, and they are a great basis for fine-tuning and for post-training work. And as the sort of next generation rolls out, I think we're going to see a even greater expansion in these kind of workloads being run at the largest companies on Earth.
And post-training kind of levels the field as well. Like at the end of the day, again, if it doesn't necessarily matter too much about what your base performance is of the model on the task, it's more about like how can we specialize and how good can it get.
Awesome. Philip, for anyone who wants to get a copy of Inference Engineering, where do they go?
So we have them up on our website. It's baseten.com/Inference Engineering, and we're doing free PDFs. And then for the physical copies, I can't keep these things on the shelves, but we're bringing them to GTC. We're bringing them to a bunch of conferences. I'm getting stuff set up so people can order them. There's a wait list. We're sending those out to people as fast as we can. It's really great how much demand there is for this book. It's very fulfilling to me to have so many people want to read what I wrote, and I'm just trying my best to get more copies out into the world every day.
Great. Awesome. Thanks for being here, guys.
Thanks for having us.
Thank you.